There is a particular silence that belongs to electric flight, and it is not actually silence at all. You're standing on a hillside in late afternoon, the grass slightly damp from the morning's dew that never fully dried, the air having that specific quality of European summer evenings, where the light turns amber and the thermals that built through the afternoon are in their last useful cycle before the cooling air collapses them. The model in your hands weighs almost nothing, or rather, it weighs exactly as much as it should, which is precisely determined because you have measured the center of gravity against this specified balance point and you know that the numbers are correct. The Elapor foam of the fuselage is smooth under your fingers, molded to a finish that does not require the sanding and filling and painting that the earlier traditions of the hobby demanded. But that is also not merely decorative smoothness. It is the smoothness of a part that was designed from the beginning with aerodynamic intent, where the surface exists to do work rather than to look done. The motor is a brushless unit, 3-phase, rated at the wattage appropriate to the airframe's weight and the performance envelope the designer specified. The folding propeller hangs at rest against the fuselage, 2 blades that will unfold at speed and fold again when the motor stops, reducing drag in glide mode to nearly nothing. You arm the electronic speed controller with a prescribed throttle sequence. You feel the motor test chirp through the airframe, 3 brief pulses that confirm the ESC is initialized and the motor phases are in sequence. The propeller does not move. The model is as silent as something with a motor in it can be. You launch. The motor comes to life with the throttle advance, not the bark and reek of a 2-stroke glow engine, not the shriek of a piston at high RPM, but the rising hum of an electric motor accelerating through its power band, clean and smooth and carrying exactly the kinetic energy the design called for. And the glider climbs. The angle is shallow. You're not forcing altitude. You're earning it, translating electrical energy into height at the rate that the motor efficiency and the glider's lift-to-drag ratio allow. And when you find the thermal you were watching, when you feel in the transmitter sticks the subtle change in response that rising air produces in a glider's behavior, you reduce, throttle, and let the aircraft work the column. And then it is quiet. The motor has stopped. The propeller blades have folded, and the aircraft circles in the rising air, in the specific patient silence that is the whole point of this particular pursuit, and you're watching it against an amber sky. And somewhere in that silence is everything that Multiplex Model Sport GmbH spent 60+ years learning how to produce. The question worth sitting with, before the full history, before the economics, before the specific corporate decisions that eventually changed what the company was and what it could offer, is this: did Multiplex change the hobby of radio-controlled aviation, or did the hobby change around it? If you know that silence, if the image of an electric glider working a late afternoon, thermal against a European sky, is something you carry, take a moment to like this video and subscribe, not for the algorithm. But so stories like this one don't fade into the digital noise, the way a thermal can dissipate into cooling air. The thoughtful, engineering-driven corner of the RC hobby deserves documentation, and keeping it visible requires people who value it to say so. The glider culture of post-war Europe was different from the model aviation culture that developed simultaneously in the United States. And the differences were not merely of scale or equipment preference. They reflected genuinely different relationships between the hobbyist and the air. American RC aviation in the 1950s and 1960s was organized predominantly around powered flight, around the glow engine and the control line model and the gradually improving radio systems that made free-flight radio-controlled aircraft progressively more accessible and more capable. The aesthetic was performance. How fast, how aerobatic, how loudly the engine announced itself across the flying field. This was a culture of mechanical expression, of the combustion engine as both tool and statement, of the model aircraft as a demonstration of what power and skill could accomplish together. It was a culture that produced extraordinary pilots and extraordinary machines. And it was also a culture that valued volume, the sound of a well-tuned engine at full throttle as a form of achievement in itself. The European glider tradition was quieter in every sense. Germany, Austria, and Switzerland had long traditions of full-scale gliding that extended back to the interwar period when gliding became both a sport and a substitute for the powered aviation that the Versailles Treaty had restricted. The slopes of the Swabian Alps, the Bavarian highlands, the ridges of the Black Forest. These were places where full-scale gliders had been flying since the 1920s, where the culture of soaring had been built into the outdoor recreational identity of the region over generations. Model aviation in this environment grew up alongside and in relationship to full-scale soaring, and the values of the soaring community, patience, precision, the development of judgment about air masses and thermal conditions, the specific discipline of finding and working rising air, transferred to the model hobbyists who share the same slopes. And this transfer of values was not merely philosophical. It was practical in ways that shaped the specific technical decisions that European model aviation culture made through the 1960s and 1970s. A pilot who had spent years learning to read the wind on a slope, who could look at the angle of the grass bending in the breeze and tell you where the lift band was, and how wide it was, and how far upwind from the ridge you needed to fly to stay in it, brought that knowledge to model aviation with them. The model became a tool for extending that practice into situations where the aircraft's size and durability made experimentation possible that full-scale flying did not allow. You could fly a model into the edge of the lift band and see what happened. And you could try a shallower bank angle in the thermal circle and measure the result in altitude gained or lost. You could learn in the model what the full-scale pilot learned expensively and slowly, and bring that learning back to the slope with you. The German engineering culture that surrounded this flying tradition added its own dimension. Baden-Württemberg is the region where precision manufacturing became synonymous with German economic identity, where the machine tool industry developed the tooling that made German industrial production precise, where automotive engineering developed the quality standards that made German cars the reference for the word quality in global markets. And this was the environment into which Multiplex was born, and in which it developed its design philosophy. The same culture that produced the German automotive engineer who refused to accept a bearing clearance outside the specified tolerance, produced the multiplex engineer who refused to accept a mold that produced parts fitting with anything less than the specified precision. These were not separate traditions. They were expressions of the same cultural value in different industrial contexts. This cultural context is the soil from which Multiplex grew. The company was founded in 1958 in what was then West Germany, in the southwestern state of Baden-Württemberg, the same region that was home to companies like Mercedes-Benz and Bosch and Porsche, a manufacturing culture that valued engineering precision and material quality in ways that showed up even in the smallest products the region produced. Baden-Württemberg was not a place that made things casually. It was a place that made things correctly. The early multiplex products were radio control systems, transmitters and receivers and servo systems for controlling model aircraft from a distance. Radio control technology in the late 1950s and through the 1960s was at the precise frontier of what civilian electronics could accomplish. The transistor was replacing the vacuum tube, the frequencies were being regulated, and the challenge of sending a reliable control signal from a handheld transmitter to a receiver in a moving aircraft, and having that receiver correctly interpret the signal and drive the appropriate servo was a genuine engineering problem. Multiplex approached it as German engineering approached engineering problems, systematically with attention to the failure modes, with the understanding that the system had to work reliably in conditions that were not laboratory conditions, in electromagnetic noise from other transmitters, in the vibration environment of a running model aircraft, in the temperatures that a model aircraft's interior experience on a summer afternoon at altitude. The radio systems that Multiplex developed through the 1960s and 1970s earned a reputation for reliability and for the specific engineering quality that made them the preference of serious pilots who could afford to have preferences. And the glider pilots of southern Germany, who were flying long-duration models over the slopes and thermal fields of the region, needed radio systems that worked correctly every time, not most of the time, which was an acceptable standard for sport pilots who flew their models low and close and could recover from a momentary glitch, but every time because a loss of control on a sailplane a kilometer away and 300 meters up had consequences that the sport pilot's situation did not. The aircraft kits that Multiplex added to the catalog in the 1970s and 1980s followed the same philosophy. Wood and fiberglass reinforced plastic construction, designed with the precision that the company's engineers had learned to apply to electronics, providing the full-scale gliding tradition's understanding of what a model had to do in the air to perform well. And the Alpha series, high-performance gliders with GRP hulls and ribbed wings spanning 2 meters, represented serious model, soaring at a level that required serious pilots and produced serious results at competition. Then, in the early 2000s, Multiplex made a decision that changed the trajectory of the company and contributed to changing the trajectory of the entire electric RC aircraft category. They introduced Elapor. Elapor, expanded polypropylene, processed and molded to Multiplex's specifications, was not merely a different construction material. It was a different philosophy of model aircraft production, made physical. The traditional foam materials used in RC model aircraft, expanded polystyrene, EPS, were fragile in ways that limited their appeal to pilots who were serious about performance and durability. EPS shattered under impact rather than deforming and recovering. It could not be reliably bonded with cyanoacrylate adhesives, the thin CA that every model builder used for quick structural repairs. It was light but brittle, useful for certain applications and limiting in others. Elapor was different, and expanded polypropylene had been used in industrial packaging and automotive applications for its combination of lightweight and impact resilience, the ability to deform under load and recover its shape, to absorb energy in a crash rather than transmitting it as structural failure. And in the context of RC model aircraft, this property was transformative and a model built from Elapor could survive impacts that would shatter an EPS model or destroy a balsa structure. And the damage it did sustain was repairable with standard thin CA adhesive, which bonded to polypropylene surfaces cleanly and reliably. And The repaired surface was nearly indistinguishable from the original. After careful gluing and light sanding, the first model produced in Elapor was the EasyStar, introduced in the early 2000s, and its success was immediate and substantial. The EasyStar was a powered glider with a pusher propeller configuration, the motor and propeller at the tail, pushing rather than pulling, which meant that nose impacts did not damage the propulsion system and that the propeller was protected from the most common accident geometry. The wing was high and unswept, giving the model the docile handling of a trainer combined with the efficient glide ratio of a sailplane design. The Elapor fuselage and wings came molded, smooth, requiring no painting or surface preparation. Beyond the installation of electronics and the final assembly steps that snapped and glued the parts together. The EasyStar became one of the most popular and most widely copied designs in the history of electric RC aviation. Its combination of docile handling, genuine glide performance, crash-resistant construction, and simple assembly addressed a market that the traditional model aircraft industry had not served well. The pilot who wanted to fly rather than build, who wanted to learn soaring skills rather than construction skills, who wanted a model that survived the learning curve rather than being consumed by it. And the EasyStar was forgiving without being boring, a distinction that matters enormously in a trainer class model, where boring forgiveness produces pilots who have never been challenged enough to develop real skill. What followed the EasyStar was a catalog of development that demonstrated the creative range of what Elapor and good engineering could produce. The FunJET, a pusher jet design capable in stock configuration of speeds approaching 100 miles per hour, and in modified configuration of over 130, used the same material and the same philosophy to create something at the opposite end of the flight envelope. The Blizzard Electric Sport Glider. The Cularis, a larger powered sailplane that combined the EasyStar's accessibility with greater wingspan and consequently better thermal performance. The FunCub, a high-wing utility transport design with oversized landing gear and STOL performance that made it capable of operating from surfaces that other models could not manage. The Mentor, a giant-scale trainer. The EasyGlider series, which evolved through 4 generations over more than 2 decades while maintaining the essential character that the original had established. All of these models shared the characteristic that multiplex engineering had built into the Elapor line. The fit of parts that snapped together with a precision that surprised people encountering it for the first time. Not the approximate fit of a kit, whose tolerances had been generous because the manufacturing process could not do better, but the specific intentional fit of components, whose relationship to each other had been designed and whose molds had been machined to produce that design accurately. And the wing spar joiner that slid into its receiver with a specific resistance that told you it was fully engaged. The tail surfaces that aligned correctly when installed correctly and could not be misaligned without producing obvious visual evidence of the error. These were not accidents of manufacturing. They were the results of engineering attention to the assembly experience as a design parameter in its own right. The FunJET deserves its own account because it demonstrated something about the Elapor material and the multiplex design philosophy that the glider models did not in quite the same way demonstrate. The FunJET was a high-speed pusher jet design, a single-piece delta-wing airframe with a pusher motor at the tail, capable in stock configuration of speeds that surprised pilots accustomed to the docile performance of trainer-class models. Modified versions with more powerful motors and higher voltage battery packs, could exceed 200 kilometers per hour in level flight. This was not a model for a pilot who was still developing comfort with basic stick and rudder skills, and it was a model for a pilot who had those skills and wanted to explore the performance that Elapor's strength and density could support. What made the FunJET interesting beyond its speed was the specific way that Elapor's properties expressed themselves at the speeds it could achieve. The Delta wing required a piloting style different from the conventional wing, a higher minimum flying speed, a more aggressive relationship between angle of attack and control authority, a landing approach that looked to pilots accustomed to conventional models, steep and fast and committed. The aircraft that could survive a ground impact at those speeds, that could bounce rather than shatter, that could be returned to flying condition with CA adhesive rather than replaced. That was the FunJET, and it was that durability that made the performance exploration possible. The pilot who crashed a conventional foam model at FunJET speeds was done for the day. The pilot who crashed a FunJET was usually back in the air within the hour. The EasyGlider series represented the other end of the same engineering philosophy. The same material and the same precision applied to the design problem of making thermals accessible rather than fast passes exhilarating. The EasyGlider's aspect ratio was designed to produce a specific glide angle in still air. The wing's airfoil was chosen for thermal soaring, for the low-speed, high-lift performance that allows a glider to circle in weak lift and climb rather than descending. The folding propeller configuration allowed the motor to be used for reaching altitude without the drag penalty that a fixed propeller imposes in glide mode. All of these decisions were engineering decisions, made by people who understood the physics of soaring and who applied that understanding to a design that could be built and flown by someone who was encountering electric soaring for the first time. The field experience of a multiplex model, the actual practice of assembling, setting up, launching, flying, and recovering one, had a character that pilots familiar with the brand recognized and described in consistent terms. It felt considered. The decisions that had been made in the design of the model were visible in the way the model behaved at every stage of the experience. End assembly was straightforward in a way that rewarded attention without requiring it, a distinction that matters to pilots who had their own preferences about how thoroughly they understood the system before they flew it. The instructions were German in their precision, every step documented, every tolerance specified, every tool listed, every adjustment procedure explained in the sequence that the designer had found produced the best result. Following the instructions completely and in order produced an aircraft whose CG was correct, whose control throws were in the specified range, whose motor and speed controller were properly connected and initialized, deviating from the instructions produced results that the instructions had, if you read them carefully, warned you about. Installing the servos was tactile work. The servo bays in a multiplex Elapor model were molded to the correct dimensions for the servos the design specified, which meant that the servo installation was a matter of placing the unit in the bay, running the cable through the provided channel, and securing the unit with the screws provided in the hardware pack. No modification of the bay was required if you used the specified servos. If you used different servos, which experienced builders sometimes did, substituting higher quality units for specific applications, the bay geometry became a constraint that had to be worked with rather than around. And this was the design's way of saying, we have done the thinking, and the result is correct if you follow it. The wiring harness deserved its own attention, and the pilot who gave it that attention produced a model that flew better and lasted longer than the pilot who routed wires casually. The speed controller's three-phase wires to the motor. The power leads from the battery connector, the signal wires from the receiver to the ESC, and to each servo. Each of these had a correct routing that the design provided guides and channels for. In wires, routed correctly, could not chafe against moving parts, could not interfere with control linkages, could not create electrical interference by running alongside servo signal wires for more distance than necessary. These were the details that separated the model that worked correctly from the model that worked until it didn't. And they were the details that the multiplex engineering team had addressed in the design before asking the builder to address them in the assembly. The battery installation in a multiplex glider was a variable. The battery pack's position was the primary mechanism for fine-tuning the center of gravity, and the manual specified the range within which the battery should sit for the CG to be correct for the specified servo and receiver weights. This was elegant engineering. The battery, which had to be accessible for recharging and removal, was positioned in a bay that the pilot could adjust within the specified range, and the CG check confirmed whether the adjustment was correct. It was not, as in some designs, necessary to add ballast, because the designer had not accounted for the weight range of available components. The design accounted for it. The pilot verified it. The system worked because both parts were. The center of gravity check was the moment of commitment before flight. The CG measurement was specified in the manual as a distance from the leading edge of the wing at the root, and you confirmed it by balancing the assembled aircraft on two fingertips at that distance. Reading the result, nose down meant nose heavy, which was safe but reduced performance. Tail down meant tail light, which was faster but less forgiving, and beyond a certain point, aerodynamically unstable. The correct CG produced an aircraft that glided at the angle its aspect ratio predicted and responded to elevator inputs with the authority the designer had intended. Getting it right was not difficult. Confirming that you had gotten it right required the specific discipline of checking rather than assuming. Then the hill. The slope lift site, where the ridge catches the wind and deflects it upward, creating a band of rising air along the face that a glider can work indefinitely, as long as the wind continues. Or the flat field on a summer afternoon, where the thermals built by differential ground heating rise in columns that can keep a glider aloft for hours if the pilot can find them and work them. Either way, the moment of launch, the overarm throw that puts the model into the air with the specific velocity and angle that the design requires to establish flying speed before control authority is needed, was where everything before it was either confirmed or challenged. Correctly assembled and adjusted, multiplex model flew the way the manual said it would fly. This sounds unremarkable at all. The number of models from any manufacturer that flew exactly as their documentation suggested was not as high as the number that required significant trim adjustment after the first flight, and the number that required significant design knowledge to diagnose the adjustment needed was higher than the number of pilots who had that knowledge. The multiplex model, correctly assembled, flew correctly. This was the engineering reputation made visible in the air. The high-tech acquisition of Multiplex in 2002 was a corporate event that the hobby community received with the mixture of hope and reservation that all such acquisitions produce. Hi-Tech was a South Korean company with its own strong reputation in the RC hobby world, primarily through its servo product line. The Hi-Tech servo had been a preferred component among serious builders for years. The choice of pilots who wanted servo performance that could be specified rather than assumed. The combination of high-tech servo engineering and Multiplex's model design and manufacturing capability had an obvious synergy, and the community could articulate why the combination made sense. What acquisitions always raise, and what the Multiplex acquisition raised, was the question of what would happen to the design philosophy. Companies that were acquired for the value of their engineering culture sometimes found in the years after acquisition that the efficiency pressures of a larger organization changed the environment in which engineering decisions were made. The engineer who had been allowed to spend 3 weeks refining a servo bay design might, in a post-acquisition environment, be allowed 3 days. The material choice that cost more but performed better might, under post-acquisition margin pressure, be replaced by the choice that costs less. These were not inevitable outcomes of acquisition. They were risks that the community understood. Multiplex continued to produce models from Bretten-Gulshausen, the facility in Baden-Württemberg, where the company had relocated in 2007, its own premises with approximately 50 employees. The Made in Germany designation that appeared on the EasyGlider 4 and other models was not marketing language. It was a factual claim about a production process that remained in the same region where the company had built its engineering culture over decades. The Elapor molds were machined in Germany. The assembly and quality control happened in Germany. The engineering decisions were made by people who worked in Baden-Württemberg and who had access to the institutional knowledge of 60-plus years of German precision manufacturing. The market pressure that Multiplex faced through the 2010s was not primarily about design quality. It was about price. The Chinese manufacturers who had entered the RC foam aircraft market had studied the Elapor model, its construction philosophy, its design choices, its market positioning, and had produced competitive products at prices that the German manufacturing cost structure could not match without either accepting lower margins or compromising quality. The consumer who was making their first purchase of an electric RC aircraft, looking at 2 similar appearing models, one made in Germany at a price reflecting German manufacturing costs, and one made in China at a price reflecting Chinese manufacturing costs, had to decide whether the difference in origin justified the difference in price.
Some did, many did not.
The community of pilots who understood the specific meaning of the multiplex engineering philosophy, who could feel in the snap of a servo bay or the slide of a spar joiner the years of tooling precision that produced it, was a community that valued the premium and was willing to pay it. But it was not a community that was growing at the rate that the less expensive alternatives were growing, because the less expensive alternatives were serving the growing market of people who were encountering electric RC flight for the first time and who had no reference for what the premium represented. The question that the multiplex story poses is one that applies beyond the RC hobby and beyond the specific industrial history of one Baden-Württemberg company. It is the question of what happens when precision becomes optional, when the market develops an alternative that delivers the primary experience without the engineering rigor that the premium product invested in delivering it correctly. The glider that climbs in a thermal can be made from German-engineered Elapor with CNC machined molds and assembly tolerances held to fractions of a millimeter. It can also be made from Chinese-manufactured foam with molds of adequate quality and tolerances that are sufficient for most pilots in most conditions. Both will climb. Both will circle. Both will be experienced by a significant portion of their pilots as equivalent. The pilot who cannot feel the difference, who has not developed the precision and the sensitivity that distinguishes adequate from correct, will not pay for what they cannot perceive, and developing the sensitivity that distinguishes adequate from correct takes time and experience, both of which are in shorter supply than they used to be. This is not a statement about intellectual capacity or native ability. It is a statement about the conditions that precision appreciation requires. Repeated exposure to precision and to its absence, in contexts where the difference has consequences over enough time that the perception becomes specific rather than general. And the pilot who has flown 100 hours in a multiplex model and 100 hours in a less precisely engineered alternative knows the difference in a specific embodied way that cannot be acquired from a review or a comparison video. They feel it in the control response, and they see it in the glide angle. They experience it in the model's behavior, at the edges of the flight envelope rather than at the center. What is lost when that culture of precision appreciation thins is not simply the market for the precise product. What is lost is the community of practice that valued and transmitted the appreciation, the slow pilots who spent Saturday afternoons in the southern German hills, who had flown generations of multiplex models and who understood in the specific technical, felt way why the engineering decisions that multiplex had made were the right ones. And when that community ages without adequate replacement, the knowledge that animated it ages too, and the products that required that knowledge to be fully appreciated become harder to justify commercially. If you still fly, and if what you fly reflects a preference for precision over convenience, if you chose the multiplex because you understood what the engineering represented, or if you're curious about what that choice feels like, leave a comment below. The community of pilots who value thoughtful engineering in their aircraft is smaller than it was, but it is not gone. What keeps it alive is not nostalgia, but the continued practice of the discipline that made it worth caring about in the first place. This channel exists partly for that reason, and the record of what this culture valued and why is worth making. Return to the hillside. The grass is that specific shade of late afternoon green that only exists in the hour before sunset, when the low light brings out the color rather than washing it out. The air has the slight coolness of an evening that has not arrived yet, but is preparing to. The afternoon light is fully amber now. The thermals in their last good minutes before the evening cooling ends them. The multiplex glider is still up, still working the column, the folded propeller invisible at this distance, the model a white crescent against the orange sky, banking in the circles that a pilot works in a thermal, the inside wing lower, the model carving a path through the rising air with the specific efficiency of a design that was engineered for exactly this. The translation of rising air into altitude, the patient accumulation of height through the disciplined exploitation of the invisible energy that the afternoon sun has stored in the landscape below. From the ground, you're making small inputs on the transmitter sticks, and the model responds to each one with the precision that 60+ years of German engineering has worked toward producing. The response that is neither too much nor too little, that arrives in the time window the pilot's reflexes work in, that communicates information about the air as well as executing the pilot's intention. This is the engineering in operation, not the specification sheet, not the promotional literature, not the Made in Germany designation on the box. The model itself in the air doing what it was designed to do. The thermal is weakening. The circles are getting wider as the column spreads and loses definition. You add a touch of throttle, the motor's quiet hum returning, the propeller unfolding at speed, and the model climbs back above the level where a landing approach can begin. The battery has several minutes left. The field is below you. The light is going. Some things are worth the time they require. Some questions are worth the patience they demand. The glider knows this. The air knows this. The engineering that made both the question and the patience possible understands it without needing to say so. The motor hums. The glider climbs. The sky holds everything it always has.